Hello there, and welcome to this collection of notebooks and tutorials on machine learning for audio signals in Python. This is a course offered by Professor Schula at the Ilmenau University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we'll talk about convolutional neural networks. Our idea is to look at convolutional neural networks under the signal processing perspective and compare it to filter banks. So let's get started. So far we used fully connected layers where the input is fully connected to each node in the following layer. Convolutional neural networks use a filter kernel instead, where each node is conducting a convolution like a filter. The filter kernel is also described as a receptive field of a certain size. At each position of this receptive field, an output is produced. Then it is shifted by a distance called stride, and a new output is produced, and so on. This has the advantage that the network is less dependent on the precise location of a signal to detect or recognize. There are convolution layers for 1, 2, and 3 dimensions. For the case of the MNIST digit recognition, we will use a 2D convolution, and it's defined as this class here in PyTorch, and you can take a look at the documentation of the conv2D that applies a 2D convolution over an input signal composed of several input planes. Here, padding means zero padding at the ends of the signal, for instance the boundary of our images. For padding equals to 0, only valid points are computed, which means that the kernel does not reach over the boundaries. For instance, if the kernel has a size of 3, we need a padding equals to 1 to obtain the same output size as the input. Here we implemented a convolutional neural network in PyTorch for the MNIST digit recognition task. So we see here we have two 2D convolutional layers, and then we have a fully connected layer at the end. For the loss function, we again will take the cross entropy loss, and for the optimizer we use ADAM. When we look, we can compare the convolutional neural networks with the case of our fully connected network that we used before for the same MNIST digit classification problem, and we will see that indeed we only have a fraction of the weights in our convolutional network when compared to the fully connected layer. This is an advantage for an implementation on smaller hardware. We can then train the convolutional network as before, and here we see a disadvantage. It takes much longer to train. We need over 1000 iterations or more to obtain a good solution, when compared to only about 10 iterations for the case when we use the fully connected network. So let's go through our model. Once again, we will import our Python packages and libraries. We are going to use PyTorch. We are going to use matplotlib to plot. Here we are defining the baseline model. So this is the convolutional neural network model that we are using: 2 conv2D layers and 1 fully connected layer. Then we have our activation functions. We are also using some max pooling. So what max pooling is doing is it's calculating the maximum or largest value in each patch of each feature map, and then the results are downsampled or pooled feature maps that highlight the most present feature in the patch. So not the average presence of the feature. In that case would be an average pooling, but you can take a look about max pooling also in PyTorch documentation. Then we are defining the batch sizes for our train, for test, the number of classes that we have. So basically it's the same procedure like we did previously, but now we just have a different model which is based on convolutional neural networks. Here we are loading our training set, we are loading our test set, and here we are just taking a look at some values just to make sure we loaded correctly, and we are plotting, for example, 4 images of the a data set, and we have here a 5, a 0, a 4, and a 1, and we have the labels 5, 0, 4, and 1, and we've done this previously, so there's no new things here. Then we also build our model. We use the cross entropy loss, we use the ADAM optimizer, and then we train our model, and after training we can save the trained weights, and then we can, for example, test, and then we have here this image that it's for me it's a 5, but the prediction here tells it's a 9, so it's a wrong prediction, but in this case it's not really clear a 5, so there is a margin for interpretations and errors. If we run this cell again, and now choosing a different sample from the test set, and now we see that this is a 9 and the prediction is also a 9, so this was a correct prediction. We will now look at the 1D convolutional neural networks for audio processing, and we'll start with a 1D signal detector. We can use a one-dimensional convolutional neural network for audio processing, for example, to create matched filters and predictors, as shown in lectures 13 and 14 of advanced signal processing. So I put here the link to lecture 13 on matched filters and lecture 14 on prediction, and also the GitHub for our examples here. You can take a look. So we will construct a signal with a length 11, and this is what we are doing here. Then we can take a look at this signal. It's a ramp. We'll now add some noise and extend the length of our signal. So we added some noise and we also extended the length. Then we need to convert the signal into a pytorch type. And we write a function signal to pytorch for that case. Then we also can implement a filter similar to a matched filter using a one-dimensional convolutional layer, a conv1D, without bias and without a nonlinear activation function. For it, we need to specify a training signal, and here our signal to detect the ramp function x and the target signal y, which is the desired output of the convolutional layer, which the optimization should reach as closely as possible during the optimization or during training. So here we have our signal x and the target y, and observe that for the target y we specified a single peak, the 1, at the position the filter should detect the signal, and zeros everywhere else. This also leads to a minimization of the output outside the signal detection, which we didn't have in our closed form solution for a match filter, for example. And we will understand that more if you take these tutorials about match filter here. So we specify our convolutional detector layer given here, the detector, and we have a convolutional 1D with a 1 input channel, 10 output channels, the kernel size 11, we use a stride of 1, padding equals to 10, and we set bias to false. Observe that here padding is equals to kernel size minus 1, which leads to a causal filter, meaning all its inputs are not in the filter. This implements our linear filter as a detector. The optimization we apply minimizes the mean square error, the so-called L2 loss function. and we let the optimization run on the same ramp function as before, and we will display the output of the detector with the clean and noise signal as input. So let's take a look at the code. We import pytorch. We use matplotlib to plot. Also, we may use numpy. Here is the function to convert a signal vector as, like for example, a mono audio signal into a 3D tensor that the conv1D of pytorch expects. Here we are defining the model with the convolutional layer, one-dimensional, with the properties, the parameters that we want. Here we're defining our input signal, is the ramp function, and also the target. Then we generate our model. We define our loss function as the mean squared error loss. We define our optimizer as an ADAM. Then we will train our model, and then we will generate predictions, and here is the outputs. We see this is for the clean input and for the noisy input, and we see the peak is very prominent here. And here we see the weights. Here it was our input signal, so we have a ramp and the noisy signal. So the figure shows that the obtained weights or coefficients in pytorch, they are used as a correlation instead of convolution, and hence the plot is the time reversed impulse response. Observe that it looks indeed different from our matched filter, which was simply the time reverse ramp signal. This is because the optimization also tries to minimize the output outside the detection time point. The result of detection for the clean and noise signals are shown here. And we can observe the peak at the detection time is indeed much more narrow than when compared to the matched filter. Our last example is an audio predictor. In this case, we are going to use the mean squared error as a minimization criteria for the loss function. In this case, this does not differ from the target of the closed form formulation, and hence we obtain almost the same solution. Here, the desired target signal Y is the audio input signal X, but one sample in the future. So what we can do is, for example, we remove the last samples of our audio signal as an input, and then the target would be our audio signal, but we remove the first sample for the signal to predict one sample in the future. So we import our Python libraries. We use again our vector to pytorch. We define here the filter length equals to 12. Here we will have a convolution in one dimension. It's a very simple one, so we have one input channel, one output channel, kernel size equals to L, which is defined as 12, stride equals 1, dilatation is also equals to 1, defined here, and here we have the padding that will be dilatation times the kernel minus 1. So what we do, we will import our audio file, and in this case is a rock and roll legend from AC/DC, Back in Black. We will normalize. We will only train, just to make it faster, we will shorten this audio, and we will train just this amount of samples. So here we are plotting our audio signal, the shortened version, and here we can listen to it. So this will be our input signal that we're going to use for training. Here we're generating our model with the mean squared error loss function. Again, we use the ADAM optimizer. We then train our model. We save the weights. And now we will process, after training, we will process the full audio Signal, so it's not the shortened version, but we use the full audio and we'll make predictions based on the obtained weights that were trained on the short audio. And this is what we are doing here. Here we are plotting the original and the prediction. So we see it here. And the prediction error. And here also we see the weights, and we can listen to the predictions. So this is a very basic and simple linear predictor that we're predicting one sample in the future. To finalize this tutorial, I leave you an exercise, and this exercise is to design a sampling rate up converter for an audio signal sampled at 8 kHz to a sampling rate of 32 kHz. For the training, we would generate the 8 kHz version by using low-pass filtering and downsampling a 32 kHz version. So you can have, for example, audio samples taken from freesound.org. So the task to design the low-pass filter as described, for example, in ADSP tutorial part 8, and also upsample it using this filter. So listen to the upsampled result and see if there is some audible artifacts, if there is not enough stop band attenuation. Then you can use a convolutional neural network to interpolate the missing samples, and you can use an autoencoder and decoder structure that it's present on the next set of slides, and then you will train it on audio signals, 8 kHz sample version as the input and 32 kHz original as target. So on the next tutorials we'll talk about autoencoders, and you can then try this exercise. Then you'll just compare the result with the traditional upsampler using the low-pass filter and try to obtain better sounding results using neural networks. So this is an exercise that you can start thinking about it now, and by the end of this tutorial you can try it out. And here you can find a link to the tutorial on filters from Advanced Digital Signal Processing Part 8, and here the GitHub with Jupyter notebooks and interactive examples. So that's it for today, and see you next time.